Problem number one here for the second half of chapter 19 asks us to write the KSP expression for the following compounds. So writing the KSP expression is really absolutely crucial to your success in this part of the chapter. We're going to do it for 3 different compounds. We'll get 3 different answers, one for each compound. I think the first thing that we need to do here is decipher what the chemical formula is of these compounds from the name. So I'll look at this first one, magnesium carbonate. And I remember that magnesium ions, when they're involved with ionic compounds, form 2+ ions. And then carbonate, that's one of our polyatomic ions, that's CO3 2-. Okay, so magnesium carbonate. It looks like if I pair them up 1 to 1, I can make the neutral compound. So if I'm writing the equilibrium that dissolves or describes the solubility of that stuff, I would take the MgCO3, dissolve it to make 2 aqueous ions. Magnesium 2+ aqueous and carbonate aqueous. That's the key chemical reaction here. So all the KSP expression is the equilibrium constant for that reaction, right? So we've been talking for weeks now. Equilibrium constants are nothing more than products over reactants. I'm going to start there. That won't be my final answer, however. Oops, 3, 2-. Then I'm going to divide that by a concentration in the denominator here that I'm going to ultimately get rid of, but I'm going to put it here for right now. Products over reactants. Now I mentioned that I'm going to get rid of this. And the reason why is because for a KSP equilibrium, that stuff is always a solid. Solids do not appear in equilibrium constant expressions, do they? Pure solids don't. As long as some of the solids there, we can establish the equilibrium. We don't need to show it. Okay? So our KSP expression for magnesium carbonate is that right there. It's just the concentration of the magnesium ion times the concentration of the carbonate ion once equilibrium is reached. Okay? All right, so that's A. To erase all this and start over, see if we can have better luck potentially here with item B. So in item B, we have a different ionic compound. It looks like it's calcium phosphate, correct? And you see common theme here is that you have to do what? You have to know your polyatomic ions. Boy, if we don't know our polyatomic ions, we're in a little bit of trouble, aren't we? We have to know how to write our ionic compound equations. Now, calcium, of course, the elemental symbol Ca is also in that second group of the periodic table. So it's Ca2+. Phosphate, again, one of our polyatomic ions is PO4, but we have to remember the charge is 3-. So if I'm going to write the formula for calcium phosphate, looks like I have to do a little work. I got to make this a neutral compound. And to make that happen, I guess it looks like I need to make this a 2, make this one a 3. So if I have 3 copies, I don't like that 3, let me change it. If I have 3 copies of my calcium ion, not much better, is it? And 2 copies of my phosphate, I can make the charges balance, and I'm good to go. So when this sparingly soluble salt, or solid, dissolves in water, I'm going to make 3 copies of Ca2+, and I'm also going to produce 2 copies of the phosphate ion. Again, the KSP for that reaction is nothing more than the equilibrium constant, products divided by reactants. So again, this is always a solid, what goes here on the left, and this KSP equilibrium always a solid. because we're always talking about a dissolution of a sparingly soluble substance. That makes our life a little bit easier because, again, all we need to worry about are these ions over on the right. In this case, that's phosphate and calcium. So I write each one of them down, put them in square brackets. Remember, the square brackets mean the molarity. And it looks like since I produced 2 copies of the phosphate, I need to square that one. Since I produced 3 copies of calcium, I need to raise that one to the 3rd power. And that then is our KSP expression for that sparingly soluble salt. All right, so again, let's move on to C. So all we're doing here really is understanding what the KSP expression is all about, right? Understanding it's just an equilibrium constant for the dissolution of a sparingly soluble salt. I think if you get that, you can probably write these KSP expressions. It's not too terribly difficult because it's more or less doing the same things we've been doing for weeks now, right? We introduced it even before spring break. Nonetheless, we'll try one more. Iron hydroxide. Of course, iron is one of those weird elements. It's not IR, it's Fe, right? That's iron. We're told in the problem that we're dealing with iron 2 in parentheses, so we know it's iron 2+. Hopefully, after the pH chapter, we know our polyatomic ion for hydroxide is OH minus 1. So if I'm going to write an ionic compound involving these 2 ions, looks like I need 2 copies of hydroxide for every one of the iron. I'm going to take that solid, I'm going to dissolve it in water, and if it does dissociate into its ions, it's going to make 1 copy of iron 2+. It's also going to make 2 copies of hydroxide. If I'm going to write the KSP expression for that, I can. It's the equilibrium concentration of iron 2+ ion raised to the 1st power times the concentration of hydroxide ion squared. Easy as that. So if you get one of these on the exam, you smile, right? Because this type of problem is not too hard for you. All right, we'll move on to the next one.